Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem M coloring of a graph. Yes, and this is from the SD sheet. So what does the problem states? The problem states that you'll be given an undirected graph, yes, and an integer M. Now your task will be to determine if the graph can be colored with at max M colors. Now that is the question. And whenever you're coloring the graph with M colors, you just need to make sure that none of the two adjacent vertices or nodes of the graphs are colored with the same color. Now, if you have seen my graph series, you would have seen the bipartite graph video. Over there, the question was instead of M colors, it was two colors. So over here, we will be checking if the graph can be colored with M colors or not, right? So if it is possible, you just need to return a 1, and if it is not possible, you need to return a 0. That is the simple enough question. Now let's understand this question with the help of this graph. So imagine this is the graph, and I'm asking you, can this graph be colored with the help of three colors? And your answer will be yes, definitely. Why? Because let's imagine I say that I'm going to color 1 for this node, and I decide that I'm going to color 2 for this node. Okay. And after that, I decide that I'm going to color 3 for this node. Okay. After that, what if I decide that I color 2 for this? So if I try out coloring in this fashion, you see that none of the adjacent nodes, like for 0 the adjacent node is 3, for 0 the adjacent node is 2, for 0 the adjacent node is 1, none of them are having the same color. That is what the question stated. You need to make sure that the graph can be colored using at maximum of three colors. It's not an compulsion that you have to use three colors. It's just the maximum number of colors that you can use. So over here I can see with the help of three colors I was able to color. But what if I take M equal to 2? Can I color it? Let's see. Imagine I color this with 1 and I decide to color this with 2. Definitely this can I color this with 1? No. Why? Because this and this guy are adjacent, and you can see that both adjacents are having colors 1. So definitely not. Can you color it with color 2? Again, no, because this and this are adjacent and they are having the color 2, same color. So using at maximum 2 colors, I will not be able to color this graph. So that is the simple question. Given M, you just need to tell us if you can color the graph with M colors or not. If you can, just return a yes. If you cannot, just return a false. That's the question. Projects. A lot of you actually struggle to find ideas about projects, isn't it? So what if I tell you an academy and coach chef are bringing up an initiative where they will be actually building and deploying a live project. Now this project will be based on an idea of stock exchange. Yes, it will be based on the idea of stock exchange. Nowadays everyone knows about stock. If you haven't, you must have seen the scam 1992, the Harshad Madaki story, right? And if you haven't seen that, you must have heard it from some friend that he has won or he has profited so much or something like that. So an academy is going to build up a live project on order book for stock exchange, and this will be done this Sunday 12:30 p.m. and which will be followed up by an AMS session on importance of projects and placements, and after that they will be having a comprehensive lecture on sorting and searching. Now what you have to do is simply keep yourself free at 12:30, and the event is absolutely free. I'll be leaving the registration link in the description below, and what you need to do is you just need to download the Unacademy app, and you have to use the coupon code take you forward to unlock this event, and you should do this before 12:30 on Sunday. And if you do this, I think you're definitely going to have a perfect Sunday. So guys, do check this out because it's going to add value. So how do you solve this problem? What is the question stating? Can you color this with at max M colors? So why don't I try every possible way? And you know that if I am going to try every possible way, the best way to implement that is using recursion. So why don't I do that? So the recursion thinking should start in a way that I will try every color on every node. Think in this way. Try every color on every node. Since I have 4 nodes, these are 0 based indexing. So imagine I start up with the node 0. And what does recursion means? Tries every possible way, right? So what is the possibility of coloring this node 0? So you might be like, hey Trevor, why don't we color this with the color 1? I agree. Why don't you color that with color 1? So assume I color that with color 1. Now you might say, hey Trevor, why don't you color that with color 2? I agree, yes we can. Now you again might say, why don't you color that with color 3? I'm agreeing to every stuff that you're saying, because we can definitely start coloring it with color 1, 2 or 3, because we are trying recursion. Recursion means try every possible combo. So in recursion, the first step that we will do is we will start coloring that with color 1. So why don't you color that with color 1? Okay, so just start with color 1. And if this is successful, if I start with color 1 and that comes out to be successful, so there's no need to try out other colors. This is the possible answer. Now, since I've colored the node 0, now instead of traversing on the graph, we know there are 4 nodes. Let's travel the 4 nodes individually. So what is the next node number wise? It's 1. So go to the node 1. Now I ask you a simple question. Which color can you color the node 1? So you're currently at 1, right? Now you might try out it 1, because whenever you're writing recursion, it tries every color. Now when you try out with 1, you see you can definitely not color that with 1. Why? Because the adjacent node of 1, that is 0, is having the color 1. So this is not possible. So when you tried coloring with 1, that's not possible. So what you decide is, okay, let's try with the other color. Can I color that with color 2? And you see that if you try coloring it with color 2, that's actually possible. Yes, that's actually possible. And if it is possible, I know there is one more color, color 3, but let's not try that as of now. Let's try out the next node in the serial wise. So the next node is node 2. Okay, so I go to node 2. Now when I go to node 2, the first color that I will try is, because I'm trying every color, let's try out color 1 and let's check out can I. So when you try color 1, you see that 2 has an adjacent node 0, 2 has an adjacent node 1. So you can definitely not color with color 1. So color 1 is not a possibility. Now you decide, can you color that with color 2? So when you try that with color 2, let's see what happens. If you try that with color 2, it checks for its adjacent. 0 is the adjacent, it's having a color 1. Okay, fine. 1 is its adjacent, it's having a color 2. That's not fine. That means you cannot color with color 2. So that means we're left out with the next color, that is color 3. Let's see if we can. Just let's see if we can. So if I try to color this with color 3, can we? What are the adjacent nodes? 0, it's having a color 1, which is not 3. The other adjacent node is 1, which is having the color 2, which is not 3. So I can color with color 3. That's a practical possibility. And if it is in the serial wise, I move to the next node. Yes, you're gonna move in serial wise. So when I move to the next node, I see that the next node is node 3. So again, I'm gonna try out with color 1. Yes, I'm gonna try out with color 1. So let's try out with color 1. So when I try out with color 1, I see it is not possible. Why? Because the adjacent node is also having a color 1. So coloring it with color 1 is definitely not possible. Can you color that with color 2? Let's check that out. I can definitely not, because the adjacent node is 1 and we cannot. So color 2 is also not possible. Can you color it with color 3? So I will be like, yes, yes you can. So since I can, I try to color that with color 3. And after that, I move to the next serial number node, that is node 4. Now at this moment, yes, at this moment we see that the number of nodes were 4 and you reached the serial number 4. And whenever you reach the serial number 4, that means, why did you reach here? Because every node you are successfully able to color with some color, right? You are successfully able to color it with some color. That is why you reach the last serial node, that is 4. Hence I can say I was able to. So thereby you can return a true. Why true? I'm going to tell you. Over here, F3, which called F4, says you give me a true. So I'm going to return a true. F2, which called F3, returns a true. Now, do you remember on F1 you tried with color 2? So since you're trying every color, there could have been a possibility of coloring that with color 3. And you could have got one more possible solution, might be. You might have got one more possible solution. But the question stated, can we? The question stated, can we? So is there a need of actually trying out a color 3 on the node 1? No. So that's why returning a true is very important, so that if you got an answer by coloring with a particular color, you do not move to the other colors. So this returns true. So this guy gets a true, doesn't tries for other one and returns a true. And this guy tried with 1. Will it try with 2? Will it try with 3? Absolutely not. Why? Because when he tried with 1, he got a possible solution. Hence, he got a true. So thereby, he also returns a true. Whenever this true is returned, your graph is definitely colored with M colors. So how will the pseudo code look like? So can I say I'm starting off with a node? So why don't I start off with a node? Okay. Now what is my base case? So I can definitely say if I'm moving on serial number of nodes like from 0, 1, 2, 3, 4. So can I say if I filled up every node, I will definitely reach the node n. And if I reach n, that means why did I reach n? Because I was able to color everything. So why don't I return a true? So I returned a true, right? Now, if it is not n and if it is like 1 or 2, so in that case, what am I trying? I'm trying to color that, right? With what colors? From 1 to m is what I'm trying. Now, when will I color? You just saw, right? If it is possible to color that node, if it is possible to color, right? If it is possible to color that node, then I will color it. Probably you can maintain some color array, and you can say that the node color will be this call, right? This color. And after that, what did you do? You did call the function for the next node, next serial number node. So let's call it. And if this function returned a true, then did you try out the other color? Did you? No, you did not. So what you check is, if this function call returns a true, there's absolutely no need to go back to this for loop. You can break out by saying return true. And if it doesn't returns true, then you have to do the backtrack step. That means whatever color you did, please make sure you remove that color, because in the next step, let's imagine, just for an example, imagine this. When you tried with color 2, this guy did not give you an answer. And if this guy did not give you an answer, then you need to try with color 3, right? And since you need to try with color 3, that means you colored with color 2. So that has to be taken off, right? So that's why you take it off. So this is how the if statement will look like. And once the for is over, so just imagine once the for is over, can I say this? I tried with every color from 1 to m, and the return true never got executed. And if it never got executed, can I say it was not possible to color this particular node with any of the colors 1 to m? And if it is not possible, I can definitely not color the graph. So if you reach this line, then you're going to return a false, saying it's not possible to color this graph. Simple as that, because I tried everything and I never got it true. It was never possible to color the graph with any of the colors, so return false. That is how it is going to look. In order to understand this algorithm in much deeper, we need to solve one more example. Why? Because we did solve an example where answer was possible. Now let's solve an example where the answer is not possible. So imagine m is given as 2 and we have the same graph. So we need to check if the graph can be colored with at max 2 colors. So let's start with the node 0. Okay, because that is what I start with. Now if you follow the code, it tries the color 1 at first. So at first it tries color 1 and it sees is it possible to color this with color 1, and it says yes it is. So you color that node with color 1 and you call the next one, that's the next node in serial, so you call it as f of 1. Now you go to f of 1 and the next function call will come f of 1, right? And it say and it checks color 1. Can you color 1? Is there a possibility of coloring it with color 1? Is there? No, because both of the adjacent nodes will have a color 1. So it sees that there is no possibility. So the for loop now moves to color 2. It checks, is there a possibility? Yes, there is. So it colors this with color 2. See, it colors this. And next it calls this function, f of 2. That's the next node in serial. Now f of 2 goes and tries with color 1. Can it color with color 1? Let's see. Can it? No, it cannot. You can see the adjacent nodes are having same color. So color 1 is not possible. For loop now goes to color 2. Color 2 is possible? No, not possible. So can I say I actually tried every color from 1 to m, that's 2, and I was not able to color it. Hence, you're going to return a false. So you're going to return a false. Now, can I say this guy got a false who called from f of 1 by coloring it with 2? So isn't that very important that you make sure that this color is removed, right? Because that color has to be removed. This is the backtracking step. So this color will be removed. Now the function call was at f of 1. It tried color 1 and it tried color 2. Not succeeded. So again return of false happens. So the false will happen, right? So again the false is happening. So you will reach f of 0. Now whenever you reach f of 0, you need to make sure this color is gone. So you will make this color 0 again, right? The for loop tried with 1. Now it will try with the color 2. So when it tries with color 2, this time it will color this with color 2. And now it will try for again f of 1. And this time it will try with color 1. That is, this guy will be colored 1. And now it will go to f of 2. And both the colors, you can see both the colors will not be possible. So it returns a false. And whenever it returns a false, this time it will try for the color 2. And it will go to f of 2. And again color 1 and 2 is not possible, so it returns a false. Ultimately f of 1 tried color 1, tried color 2, did not find an answer, so returned a false. F of 0 did try 1 where he got a false. Now, when he tried 2, he also got a false, so f of 0 will also reach this line and it returns a false. So this is how the recursion works. I hope you have understood this, right? Just in case you have doubts, I'll highly recommend that you should definitely draw the recursion tree by yourself, because drawing the recursion tree is the only way in order to understand how recursion works. There's no other way, right? So if I talk about the time complexity, now you can analyze it in a much deeper level, but if I talk about the high level complexity, keeping aside the conditions, there are n nodes and I'm trying m colors on each of them. I'm trying m colors, right, for every node, because I'm trying every node. In every node I'm trying to place m colors, so n to the power m. But if you keep the conditions, like, because you're checking for possibility, then it will be much lesser than that. But if I talk about very very high level, it's n to the power m. That is what the time complexity is. And what about the space complexity? You will be using a color array to color it, and you'll be definitely using an auxiliary space. Yes, an auxiliary space of big of n. Why? Because you'll be coloring like 0, 1, 2, 3. So there will be at max auxiliary space of big of, and the depth of the recursion tree is n, not more than that. So that's how the auxiliary space will be, apart from the graph storage and all. And the time complexity will be n to the power m, because you're trying m colors at every node. So now it's time to discuss the C++ as well as the Java solution to this problem. So let's check out the Java solution. So the Java solution basically gives you the graph. And if you don't know how to store a graph, you can definitely watch my representation of graph videos in C++ as well as in Java, so that you get an idea about how to store it. They've given a color array so that you can definitely store the colors. And they've given you the starting node. In almost all the cases, it is 0. Even if you do not take the question also, like, the solution works. And over there they've given you something like m. M is basically the number of colors that you can at maximum use. So at first what I do is I find out the number of nodes, that is g dot length, and right after that I call this a recursive function solve, and I start with the node 0. This is basically node 0, and I pass on the graph, I pass on the color, I pass on the number of nodes, and I pass on m, that is the maximum number of colors. And if this recursive function returns a true, I say it is possible to color, and or else I say it is not possible to color. Simple as that. Now let's check out the recursion. Again, the recursion takes the node and all the other parameters that are required. I know this is the base case. Whenever I have colored all the n nodes, I'm going to return a true. What about the normal recursion? I'm going to try out coloring it with every m possible color. So why don't I iterate from 1 to m? So let's iterate from 1 to m. And I check, is it safe? I'm going to explain you this is safe afterwards. But as of now, just assume, is it safe? And I pass on the parameters, whatever is there. And right after that, I color it. Then I call the same recursive function. And if that returns true, I return a true. And if this doesn't returns a true, I'll definitely come back and I have to erase that color. That is what backtracking is. You definitely have to erase the color. So erase the color. And if you have tried every 1 to m color and it never returned a true, it never ever returned a true, you are definitely going to return a false, saying that it's not possible to color this node with any of the colors from 1 to m. So why don't you go back? Okay, so this is how you're going to write the recursive code. And now let's understand the isSafe function. So generally isSafe is about checking up if any of the adjacent nodes is having the same color I that I'm trying to color it with. So I take that call, that is the color, and I just traverse for its adjacent nodes. If you do int colon g of node, it easily traverses. It's a for each loop. It easily traverses for all its adjacent nodes, and I basically check if the adjacent node's color is equivalent to the color that I'm trying to do for this node. And if it is, I return saying false. No, you cannot, because the adjacent node is having the same color. Or else I'll return a true saying that yes, you can, because none of the adjacent nodes is having the same color. Once the entire function is done, you can definitely return a false. If none of the combinations return you a true, you can definitely return a false over here. And this is how the code for Java will look like. So we're going to discuss the C++ solution, but if you don't know how to store a graph, you can definitely watch my C++ representation in a graph video so that you have a fair bit of idea how to store a graph. Okay, so I'm assuming you know how to store a graph. So what they've given you is the graph, and M, which is the number of colors that you can use at maximum to color a graph, and INTN, yes, which is the number of nodes. So what I do is I assign a color array, and I make sure that it is completely assigned with 0. That means none of the nodes are colored. And what I do is I start with the starting node, assuming that this is 0 based indexing. I start with the node 0, and I pass on all the other parameters that are required. And this is basically the recursive function f of 0. And if this recursive function returns a true, I'm going to return a true. That means it's possible, or else I'm going to return a false. Now let's check out the recursive function. What about the recursive function? I have this recursive function, takes the node and takes all the other parameters that will be required. I initially made sure the base case was if I have colored all the n nodes, I'm going to return a true, or else I'm going to try every color from 1 to m, and I'm going to write this isSafe function. I'll explain you the isSafe function afterwards, but assume it's an isSafe function which tells you true if it is possible to color it with that color. That means none of the adjacent nodes have the same color. Then I color it with color I, and I call the recursive function again for the next node, that is node plus 1. And if this returns a true, I return a true. Or else if this doesn't returns a true, I made sure that whatever color I did, I just take off that color. That's backtracking. I take off that color. And if I've tried out every color from 1 to m, yes, if I've tried out every color from 1 to m, and I find that it was not possible, yes, I find that it was not possible to color it with any of the m colors, I'm going to return a false. That's how the recursive code will look like. But now, what about the isSafe code? How is that isSafe code going to look like? So what I can say is the isSafe code is going to look like something this. isSafe takes the node and takes the graph, takes the color, and takes the color that I'm trying to do that node. Takes the color that I'm trying to do that node, right? So what I do is I traverse for all its adjacent nodes. That's from 0 to n in the matrix, and I see that if it is not this node itself, and what I do is I basically check a graph of k node, basically the adjacent. If that is 1, that means there is an edge. That means it's an adjacent node. So if it is an adjacent node and the color is equivalent to the color that I'm trying to do, that means it's not possible, because the adjacent node k is having a color that I am trying to do. So why don't you return a false? Simply return a false. And if none of the adjacent node was having the same color call that I was trying to do, you have to return a true, saying that it is safe to color that with that color, because none of the adjacents are having the same color. Once this is done, either this guy will return a true, that means it is possible to color, or else it returns a false, which means you return a false saying that it is not possible to color. So this is how your C++ code will look like. So guys, I hope you have understood the entire explanation, and just in case you did, please make sure you like this video, and if you're new to our channel, do consider subscribing to us. It will be of great support. Okay, so with this I'll be wrapping up this video. Let's meet in the next video, where I will be discussing the next problem from the SDE sheet.